In the 1930s, telecommunications ran on physical copper and human labor. Thousands of operators sat at massive switchboards, manually connecting lines to route calls across the country. As the telephone network expanded, this manual routing became impossible to scale. The solution was the electromechanical relay, a physical switch triggered by an electrical current that could route calls automatically, creating sprawling networks of clicking metal. Engineers began leveraging these automated switches as physical logic gates, using the pulse of one electrical relay to trigger the next, in a rudimentary cascading chain of command. In 1937, Bell Labs engineer George Stimets took this concept to its logical conclusion. Working at home, he wired together scrap relays from the telephone company to create what he called the Model K adder. Built entirely on his kitchen table, the Model K successfully demonstrated that telephone relays could perform binary addition. At the exact same time in Germany, engineer Konrad Zuse was achieving parallel breakthroughs, building his Z2 computer using the same telephone company relays. But building a proof of concept on a kitchen table is very different from engineering a national grid. The physical design of these intricate control circuits was treated as an intuitive art. There was no rigorous scientific method for arranging them. Engineers built unoptimized, redundant protective circuits through sheer trial and error. This resulted in massive physical costs in raw materials, towering racks of equipment, and a high potential for catastrophic failure if a single relay misfired. The solution to this engineering crisis arrived in 1938 in a master's thesis published by a 21-year-old MIT student named Claude Shannon. Shannon proposed a theory of isomorphism. He recognized that the physical on and off behavior of electromechanical relays perfectly mapped onto the calculus of propositions, a system of formal logic invented by George Boole nearly a century earlier. By proving this structural equivalence, Shannon took an abstract branch of philosophy and turned it into an algorithmic tool to blueprint and optimize physical machine hardware. Shannon standardized circuits based on hindrance, which we now call impedance. The symbol 0 represents a closed circuit, where there is zero impedance to the current. Conversely, the symbol 1 represents an open circuit, meaning infinite impedance completely blocks the current. With these two states defined, Shannon analyzed how switches are wired together, starting with series connections. Looking at Figure 2, he proved that connecting two terminals in a series maps directly to logical addition, represented by a plus sign. If an electrical current is flowing through a series and encounters even one open switch, a 1, the entire path is broken. Therefore, 1 plus 0 equals 1. The circuit is open. Next, he evaluated the alternative, wiring circuits in parallel. Moving to Figure 3, a parallel connection maps directly to logical multiplication. Because current always seeks the path of least resistance, a closed switch in parallel with an open switch will still let electricity flow. 0 times 1 equals 0. The circuit remains closed. Modern digital logic actually reverses this convention using admittance. Today, a 1 represents a closed active circuit, while a 0 represents an open inactive one. Regardless of which state is assigned 0 or 1, Shannon's definitions establish a strict set of formal postulates governing the behavior of any switch combination. As outlined in the postulate section of his paper, physical electrical routing exactly mirrors Huntington's established mathematical postulates for symbolic logic. By establishing this strict translation dictionary, engineers no longer had to rely on trial and error or visualize the physical flow of electricity. They could design complex hardware by manipulating pure Boolean equations. This theoretical framework provided an immediate solution to the standard engineering dilemma of the era: sprawling circuit bloat. Consider this highly complex multi-relay network in Figure 5. The goal is to simplify it, saving space and materials. Optimizing this physically was exhausting, but using Shannon's system, the layout translates directly into this massive, intimidating algebraic hindrance equation. Attempting to simplify a circuit of this density mechanically by merely looking at the schematic and guessing which switches are redundant is nearly impossible. However, with Boolean logic, we can apply high-speed algorithmic reduction. We start by multiplying out the terms to expand the equation, then apply the distributive law to factor the expression, grouping redundant variables together. Then we apply logical negation. Because a variable plus its inverse always equals 1, we can completely eliminate these redundant relays. After systematically applying these theorems, we are left with a final, highly factored hindrance equation. We have taken a massive string of variables and reduced it to a sleek, hyper-efficient expression. Finally, we translate this simplified equation back into a physical schematic, shown here in Figure 6. The new circuit has a severely reduced number of physical elements and relay contacts, yet it maintains the exact same operational output as the sprawling original. Algorithmic synthesis mathematically guarantees a circuit with the absolute minimum amount of physical hardware. Optimization was no longer a guessing game, it was a solved problem. Despite this success, Shannon had to address a critical limitation. Basic series parallel equations cannot describe every type of physical routing. In the real world, telecommunication networks often utilize multi-terminal or non-planar topologies, where electrical current can flow in multiple directions simultaneously. The primary obstacle to standard Boolean analysis is the bridge circuit, shown here in Figure 10. Reading logic strictly from left to right fails on a bridge circuit because of the central routing node, which allows current to cross between the parallel paths. Shannon found a brilliant workaround by borrowing transformation formulas from standard alternating and direct current network theory. By applying a star-to-mesh transformation, he could break the bridge apart algebraically. Isolating that central node allows the physical block to be bypassed. The complex bridge topology cleanly transforms into an equivalent, highly solvable series parallel equation. This step-by-step mathematical proof culminates in Table I of Shannon's thesis. Here is the explicit prove-it equivalence between physical circuit states in the left column and propositional logic in the right column. Table I represents a definitive synthesis, the recognition that hardware is a physical implementation of logic. It meant that any operation defined in the realm of symbolic thought could be encoded directly into the arrangement of copper and steel. By unifying Boolean logic with electrical engineering, Shannon provided the mathematical tools necessary to design the complex switching systems that would define the next century of computing.